place where it is walled off from the rest of the body, and for them, it's physically impossible to unleash it on themselves. And finally, you could store your toxins in an inactive form, like the slow loris, the world's only venomous primate, does. The toxin the loris secretes from its armpits is completely harmless on its own. It's only when the animal licks its armpit, putting the venom in contact with saliva, that the venom becomes activated. And when the loris subsequently bites an enemy, that venom gets transferred to the bite wound, where it causes the victim's flesh to rot away. In other words, if you're going to be venomous or poisonous, use protection. Rip currents typically move 1 to 2 feet per second, with the fastest topping 8 feet per second, and most of them can easily overpower even the best swimmers and carry them away from shore. So even if you're Michael Phelps, don't even think about trying to swim against a rip current. There are, however, 2 potential escape routes that beach safety experts recommend if you're ever caught in one. Because rip currents are often pretty narrow, one option is to swim parallel to shore and out of the current. But if swimming to one side isn't possible, possibly because of exhaustion, another option is just to let the rip current carry you, which sounds terrifying. But rip currents don't run forever out to sea, they tend to fan out as they move away from the beach. So if you can float or tread water long enough, you're likely to meander back into the waves and get pushed to a sandbar, where the water is likely shallow enough to stand. Scientists can measure dinosaurs' temperatures thanks to a tough crystal-like mineral that accumulates in bones and teeth, known as bioapatite. Bioapatite contains mostly carbon and oxygen, but not all of those carbon and oxygen atoms are the same. Heavy isotopes, specifically C13 and O18, have a stronger attraction to each other than they do to the more common, lighter isotopes of carbon and oxygen. So when these atoms come together to form minerals, they don't stick together randomly. Instead, these heavy isotopes are more likely to end up bonded to each other than they otherwise would be by random chance. But if we crank up the heat, the heavy isotopes have less of a chance to bond with each other. So bones that form at warmer temperatures contain fewer bonds between heavy carbon and heavy oxygen than bones formed at cooler temperatures. Let me say that again. The fraction of bonded together heavy isotopes in a sample of bone can serve as a record of how warm or cool the bone was when it formed. It's not sticking a thermometer under a dinosaur's tongue, but it might be the next best thing. And that's how we know that T-Rex had a body temperature of 38 degrees Celsius. Earthworms eat leaves and then poop their way around underground, returning nutrients to the deep soil. But some plants, and even whole ecosystems, are actually better off wormless. For several thousand years, the forests of northern North America grew tall and thick, in part because there were no worms. Without earthworms to munch fallen detritus, leaves piled up in thick layers, which protected young tree seedlings from frost and herbivores, and also prevented the tree's competitors, smaller, sun-loving plants, from pushing their way through. But then, in the 1800s, some European wrigglers arrived, perhaps as fishing bait for other new immigrants, and invaded the surrounding woods, where they immediately started devouring the layers of leaves that had built up over the years. This moved nutrients from the leaf layer to the deeper layers of soil, where it's harder for young tree roots to reach, and left tree seedlings exposed to the elements. As a result, when old trees died, there weren't as many young trees to replace them, meaning that many old forests are starting to get replaced by grasslands.
One of the main goals of AI is to automate tasks, often things that humans can't or don't want to do themselves. So the AI models are built to be capable and independent. But they're getting so powerful and so autonomous that many experts are convinced that soon AI will become far more capable than any person, corporation, or even nation. They'll attain what scientists call superintelligence. They'll be able to accomplish their goals in ways we humans can't anticipate, and even come up with their own goals. And since so much in our lives is connected and controlled by computers, a super intelligent AI could conceivably hijack those computers, thereby controlling almost everything. But what kinds of real-life, civilization-ending scenarios are experts actually worried about? One example you might have heard about is the so-called paperclip maximizer problem. The gist is that an AI that's given computer control over a smart factory and directed to make as many paperclips as possible might decide that we humans are a good source of carbon for making the steel in those paperclips and use us all up in the process. Of course, this maximization problem could just as easily apply to an AI that, in trying to muster the computational power to, say, solve the incredibly complicated Riemann hypothesis, takes over all of the world's data centers to work on the problem, and then takes over all of the world's electrical grids and directs them to send power to the data centers, which uses up all of the energy in the world, plunging humanity into chaos and darkness.
Hyenas look a lot like dogs, but evolutionarily they're more closely related to cats. Scientists lump them into a group of cat-like carnivores that also includes civets. Hyenas' closest relatives are actually mongooses and meerkats. But hyenas are weird enough that they're in their own taxonomic group, Hyaenidae, which includes 4 living species. The famous spotted hyena, the solitary striped hyena, the mysterious brown hyena, and the tiny and adorable aardwolf.
math helped me win a game show. At the Comic-Con, I joined a pop culture game show with trivia questions, a bit of public humiliation, and, ultimately, a math problem. The final game in this show was a game of chance. I had to choose 1 out of 3 boxes, and only one of those boxes had a prize. Then, the host opened an unchosen box and showed that it was empty. He then asked me whether I wanted to switch boxes. At this moment, I realized that I was part of a famous math problem, the Monty Hall problem, in real life, which was super exciting. And before you say, Lisa, you're a nerd, I was at a Comic-Con playing a pop culture quiz dressed in a Warhammer costume. Being excited about math isn't even the nerdiest thing that's going on in this scenario. Anyway, about the game. I knew I had to switch boxes, and this is why. When I made my original choice, there was a 1 out of 3 chance that I would choose a box with a prize in it, but a 2 out of 3 chance that this prize would be in one of the other boxes. When the host took the empty box out of the equation, there were 2 boxes left. This makes us feel like the odds are now 50-50. But it's not. It's still about the original 3 options. The odds remain the same, 1/3 for your box and 2/3 for the other 2. What did change is that the 2/3 are now concentrated into 1 box instead of 2. It's like that box is now heavier with chance. So the moment the host showed me that 1 box was empty and allowed me to switch boxes, he gave me a chance to switch bets and increase my odds. And that's how...
A world without predators. It sounds like a safer, happier world, but come on, this is science. The only way to really know what would happen would be to do a large-scale experiment that takes a big swath of relatively pristine habitat, divides it up into lots of replicates, removes the top predators from some, and... you get it. But luckily, we don't have to go to these great lengths because someone already ran this experiment for us, accidentally. Find out how in our full video below.
On a recent hike, I came across a beautiful little lake and I saw something that totally surprised me. A fish. Which, okay, on its own, isn't particularly weird. But this lake, an alpine lake high in the Rocky Mountains, was miles away from any other bodies of water. How in the world does a fish get somewhere like this in the first place? There are 3 main ways that fish can get into seemingly isolated lakes. First, when it rains a lot, lakes that are normally isolated can overflow and get connected by temporary streams. This allows all sorts of stuff, including fish, to get from one lake into another. Maybe it parachuted in, which sounds absurd, but many wildlife agencies in the US and around the world literally dump fish out of planes into mountain lakes to provide food and fishing opportunities. It's yet another of the many ways humans move species around on Earth, which has all sorts of ramifications. And while I guess it's possible that someone somehow brought the fish up there and released it, there's one other way weirder and grosser hypothesis to consider. It got pooped out. Or at least, it's the descendant of fish that did. See, there are all sorts of animals, like bears and beavers and birds, that do regularly move from lake to lake. At least one of those species, the mallard duck, has a particular fondness for fish eggs. And a recent study found that out of every 1,000 eggs that a duck eats, about 2 survive the duck's digestive tract. Because ducks can fly up to a few hundred miles between the eating and the pooping, they can unwittingly Uber baby fish into super remote lakes.
Now is a great time to be a black bear in America, thanks to 2 lucky breaks. First, North American hunters have mostly stopped hunting black bears since the bears have become a symbol of cuteness rather than of ferociousness. Second, as North Americans moved from farms into cities over the last century, the new growth forests that popped up in the old fields happened to be the perfect habitat for bears. Things are so good for the black bears that there are now about twice as many of them roaming the woods of North America as there were when European colonists first arrived 500 years ago. Want to learn more about how some species get lucky while others get shafted? Check out the video below. Lunar eclipses, that is, when a full moon completely enters the Earth's shadow and turns red, were the key to spotting eclipse patterns. When the moon passes into the Earth's shadow to create a lunar eclipse, the event can be seen from the entire nighttime half of the planet. When the moon casts its shadow on the Earth during a solar eclipse, the eclipse can only be seen from within the moon's shadow. So astronomers would see roughly half of the lunar eclipses that happened, as opposed to only a handful of solar eclipses. That gave the astronomers enough data to figure out that lunar eclipses seem to repeat every 18 years, 11 days, and 8 hours, a pattern which we now call the Saros. And it turns out that the Saros also applies to solar eclipses. If a solar eclipse happens here, another one with a similar path will be visible 18 years, 11 days, and 8 hours later. However, because of those extra 8 hours, the Earth will have rotated 120 degrees farther around, and the eclipse path will be shifted 120 degrees westward of the last one. What if animals had their own podcasts? Now, hear me out. Geese could listen to The Morning Squawk, where a cranky gander could share migration traffic reports. Humpbacks